Welcome to this presentation on a synergistic approach to predictable compilation and scheduling on commodity multicores. Multicore embedded systems enable new high-compute workloads to be executed in the embedded domain. However, many of these workloads require strict timing real-time guarantees. This requires us to bound the execution time in advance. However, this becomes problematic in multicore systems due to resource sharing. In the single-core case, we knew the latencies of every single part of an access to every single part of the memory hierarchy, and we could compute every execution time in isolation using known analytical techniques. However, as soon as we add another core to the system, we have to differentiate between private and shared memory. The private memory still has this property, but as soon as we go into the shared memory, we have the problem that two cores can cause interference to each other, increasing the latencies. Thus, we have to take this into account when computing our worst-case execution time, and unfortunately there are no good techniques that allow us to do this with tightly bounded execution times. Unfortunately, again, this becomes a bigger and bigger problem the more cores we add. For this reason, we need software techniques to solve this problem. One such technique that has been proposed is the predictable execution model. Through scheduling techniques, this aims to remove this term completely from the calculation, returning us to the single-core equivalent case where we can use traditional methods to compute the worst-case execution time. Now, how this works is that there is the realization that task execution consists of two parts: memory accesses when we miss in the cache and local computation when we hit in the cache. Typically, these are spread out in small chunks over the course of the program, and every time many cores execute a cache miss at the same time, we have this interference problem. Now, the good thing is that this is limited to memory accesses. So what the authors of the predictable execution model realized is that we can simply group all of these memory accesses together in chunks that are big enough to schedule independently. We call each block of these memory accesses a memory phase, and we use it to prefetch data to the local memory where we do the computation in a correspondingly named compute phase. Now, if we schedule a single memory phase at a time, we avoid the interference problem altogether, enabling predictable execution on commercial off-the-shelf system through transforming it into a scheduling problem. Now, the execution time, which we have now greatly simplified, is not the only thing we have to care about. We also have to care about the total response time. The total response time, of course, also depends on the execution time, but also on the core blocking time, for example, if we are preempted. But new to prem, we also have to take into consideration the memory blocking time because we have this mutual exclusive access to memory. In effect, we're taking the interference from the cores from the previous execution time equation and putting it into the memory blocking time of the schedule. And of course, we also have to take into account the scheduling overhead. All of this together is required for certification processes to guarantee that we are meeting our real-time requirements. Now, prem requires code to be refactored, and this is typically done by a compiler. All of the state-of-the-art compilers that are available today take a piece of code and break it down into chunks corresponding to the single entry, single exit regions of the code. Now, this allows us to build chunks of the code, which can then be used as the atomic unit for selecting prem intervals. To do this, we must of course also know the size of each of these chunks, which is computed by the compiler through static analysis. Now, we can make any combination of these chunks into an interval as long as m and n and k in this case are smaller than the local memory. If the combination of all are smaller than the local memory, we can make all of them into the same interval or any other combination that we might like. Now, inside the compiler, this is transformed into the separate memory here in prefetch and write-back phases and the computation phase. And of course, for each of these phases, we require a scheduling decision because we need to take ownership of the memory hierarchy. This is of course not for free, and therefore the compiler tries to amortize this cost by selecting large intervals. Going back to our previous calculation for the response time, we maximize the per interval execution time to amortize the scheduling overhead. Now, optimizing the single program by selecting larger intervals is of course good for the performance of that task, but it gives the scheduler a very coarse granularity to schedule the entire system. Considering, for example, if we have two tasks, tau 0 and tau 1, which are released at the same time, if tau 0 takes a long time to complete its prefetch phase, tau 1 has to stall entirely until it can take ownership of the memory. This can lead to a case where we have a quite high response time and very low utilization considering tau 1. If we instead allow the scheduler to have more freedom by selecting smaller intervals in the compiler, we can have much less of this idle time and overall a shorter response time. So by improving the response time here, we traded off the performance of the single task tau 0. So again, going back to our computation of the response time, we see that if we minimize per interval execution time, we can also minimize the memory blocking time, leading to a tighter schedule and better response time. Now, we see that the execution time per interval here, we have two conflicting goals. We want to maximize, with the interval selection in the compiler, the execution time to amortize the scheduling overhead, but we want to minimize it in the scheduler to have a finer granularity at which we can construct the schedule. So what is the correct trade-off here? And perhaps more important, when to make the trade-off? Now, what we can observe here is that intervals are selected during compilation, at which time we don't know the response time because this is only known after scheduling. So there is an unmet dependency to fulfill this trade-off. And this makes it impossible to schedule well-optimized prem systems with current techniques. And this is what we address in this work. So, going to the original compilation and scheduling flow for prem, we go from the source code and produce a binary using the compiler. We also measure or analyze the worst-case execution time of each interval, which we are then scheduling. Combining this information with the real-time constraints and some metadata about the program from the compiler, we get the system schedule and the binary code. Now, of course, this system schedule is susceptible to the suboptimality from the interval selection discussed previously. This is where the synergistic compilation and scheduling comes into the frame. We do this with a new optimizer, which translates the scheduler output, the response time, to a format understandable by the compiler to select better intervals. But how? By passing the regions from the compiler to the optimizer is able to deconstruct the intervals that were used for scheduling into their constituent parts. It then can reselect intervals by passing an overruling vector to the compiler that overrules the internal heuristics for interval selection. We have implemented this in a genetic algorithm, and it encodes two types of intervals. First, for non-loop intervals, we use the familiar representation from before, and we decorate it with Boolean values, which allows us to encode how intervals are selected in a binary string. This, in turn, is the overruling vector. Having the overruling vector 1, 1, 0, 1 here means that B0 and B1 connect an interval as such, and the 0 at B2 means we split an interval and then connect with B3 a new interval. This gives us a way to transform regions into new intervals. Now, for loop regions, we have a very similar setup, but for the loop region, region 7 in this case, we do not assign one of these binary values. The reason for this is that if this loop is larger than what fits in the local memory, we have no way of selecting it with any of the surrounding regions anyway. Instead, we express the iterations of this loop using the parameter G0, which tells us how many iterations should we unroll of this loop into an interval. This gives us a new encoding where the center bits here encode the unrolling. So having the first bit set to 1 means that we select R5 and R6 into an interval, and the last one corresponds to B5, same thing, and the 3 in the middle corresponds to G0, which is unrolled into 3 intervals. Now, we also have to take the response times into account, and this is where the genetic optimizer comes into account. Using an example here shown at the top of the screen, we represent these regions into intervals with the string 1101. Now, using the mutation operation, we can randomly change bits in this. That gives us a new representation in intervals and thus a new interval selection. We can mutate again to get a completely different selection. Additionally to mutation, we also do the crossover operation, where we randomly select one of the bits from the two parents into the child and get yet another interval. Using these operations, we can explore the solution space and assign a score to them. In this case, we assign the fitness score as 1 over the response time, meaning higher is better. So if we have now these fitness scores for each different interval selection, we can deselect the worst of them and select the highest one and return this interval selection in our overruling vectors, thus having an interval selection that gives a better schedule. So, using this approach, we detranslate the intervals back to regions, make a new selection, passing them to the compiler, and which intervals we pass to the compiler is dependent on which one performs best under scheduling. To evaluate the proposed methodology, we use benchmarks. We use 3 different BLAS kernels of different compute communication ratios, the memory-bound AXB, the medium matrix vector multiplication, and the compute-bound matrix-matrix multiplication. Additionally, we use benchmarks from the polybench benchmark suite of different compute-to-communication ratios. We pass this to the proposed optimizer toolchain and execute them on the NVIDIA TX2 on the ARM A57 cluster. Now, the setup here is that we use one core for one task and another core for another task, so we always execute these benchmarks in pairs. And since we want to control access to the shared memory hierarchy, we use a memory arbitrator, so each task before accessing shared memory requests permission from the arbitrator. We migrate all other processes in the system to another core, and since these are not really accessing memory, they are not causing any problems. Now, since we evaluate these pairwise, we divide these pairs into 3 different classes. First, we have symmetric scenarios where we execute 2 instances of the same benchmark. Correspondingly, we have asymmetric benchmarks where we take the same benchmarks but under every other combination. For these, we'll present the full solution space and provide a few insights. For the other combinations, we will show the improvement over the traditional approach. Now, all of these benchmarks are designed to finish in 0.8 seconds. So if we have 0 memory blocking, that means that the scenario will also finish in 0.8 seconds. So let us begin with the solution space exploration. Starting with the symmetric scenarios, we can see the plots here with the vertical axis having the execution time of the scenario and the 2 horizontal axes showing the unrolling factor for each of the benchmarks. The reason we plot these solution spaces based on the unrolling factor is that these benchmarks are loop bound, and therefore we select the best possible configuration for each loop granularity and plot them. The compiler heuristic of selecting the largest interval possible is represented by the point in the 3D plot closest to the screen, the largest unrolling factor, because it selects the largest possible intervals. In the cases where, in the 2 first cases here, we can see that the compiler heuristic actually finds the best solution. However, in the matrix multiplication scenario, we see that we've actually found a better solution by reducing the interval size of one of the 2 instances of matrix multiplication. Looking at the asymmetric scenarios, we see that the plots now have an angular shape, and the reason for this is that we find local optima where the computation time of one overlaps a little bit better than the surrounding points with the memory phase of the other task. In all of these cases, we are able to find a better solution by reducing the interval sizes of one of the benchmarks. Having a look at the overall scenarios, we plot the response time on the y-axis and all of the scenarios listed on the x-axis. The yellow bar represents the compiler heuristic found solution response time from scheduling, and the optimizer is represented by the blue bars. We see here that we have a group of scenarios where we are able to improve the response time by up to 31%. These are scenarios which have a quite high degree of memory boundedness, but enough computation in them to allow us to find good overlapping between computation and memory so as to make continuous progress. For many of the other scenarios, we are still able to see a significant improvement of about 10%. And of course, as we saw, there are 2 scenarios shown in the previous plots where we are not able to find a better solution than the compiler. Overall, we are able to improve the response time by 12%, but taking a step back and considering that if we have no memory blocking time, the expected response time is 0.8 seconds, we can see that we are actually able to remove 50% of this memory blocking time, leading to much better schedules thanks to the optimizer. So in conclusion, we have observed that scheduling optimality depends on prem interval selection, but because the interval selection and the scheduling are disconnected, these 2 tools are by themselves unable to create an optimized system. Therefore, by using current techniques, you will never be able to reach the optimum even if you have individually optimal schedulers and compilers. Therefore, we propose a synergistic methodology for both compilation and scheduling based on a new prem optimizer which solves this problem, as we saw in the key results, having a 12% average improvement in response time and up to 31%. Thank you very much for listening. Thank you.